There we go. Okay, so we've talked about maximum and minimum last time. We talked about graphing quadratic functions. So given given a quadratic function, here's what you need to be able to do. So this is 3.1 summary. Given a quadratic function, f of x equals, and then there's the normal form of it, ax squared plus bx plus c. Know how to convert it into this form. Know how to convert it into this form. So this is so-called standard form, or possibly even vertex form is what I like to call it. Know how to interpret that form. Namely that, what do I mean by that? The vertex is at h comma k. So recalling that when you get it into this form, you know, the thing that's being subtracted inside, that's the x value. So if, for instance, if it was x minus 2, then the x value of the vertex would just be a 2. Whereas if it was x plus 2, then the x value of the vertex would be negative 2. So you've always got to make sure that sign is flipping for that h letter. In other words, for the x coordinate of the vertex. And then, of course, there's the y coordinate of the vertex. What else do we need to know to interpret this? The sign of a, that term up front, which is the same a from here. You notice whenever we did our problems where there was a non-1 leading term, like I did a couple on Monday, where there was like a 5 or a -1, that is the same letter a that is happening in this form as well. So the sign of a, what is there to interpret from there? Well, it determines whether the parabola points up or down. Let's see, we also need to know how to find y-intercept. And to do that, you just evaluate f at 0. So you literally plug in 0 into the function and just see what the output is. That will be your y-coordinate of your y-intercept. And also know how to find x-intercepts, which is a bit more complicated. That's where you set the function, the whole output function, so this a times x minus h all squared plus k equal to 0, and solve for x. Right, and that can be quite a process. Sometimes there aren't any at all, right? But it's still kind of a process to show that there are not any. And then finally, the last thing we did. I'm forgetting something else. Okay, there's 2 more things. Know how to find domain and range. Whoops. Recall that the domain for any polynomial function, and including quadratic functions, the domain is just unbounded, completely unbounded, negative infinity to positive infinity. That's what it'll be for every polynomial function. The range, however, is going to be, it is cut off, right? It is bounded. It's going to be like this sort of shape. And what is that y value? What is that y value for the range? And this is not the only kind of shape, right? It might be this, or it might be this shape as well. Either way, it's bounded on one end. And this is for, this is a range for some parabola pointing up, right? Some parabola pointing up. So if I'm thinking about how to find the range, I'm thinking about what are the y values that it hits. Well, this one has a lowest y value. This one has a lowest y value, and it's right there, right? So what is that lowest y value? Well, that would be the y value of the vertex, the minimum, right? It's all kind of coming together. There's different ways to interpret all of these things, but what I can say is I can put a k there. And similarly here, if this thing is pointing down, then your range will look like this, where the highest value is up at the vertex. Either way, that extreme value, either minimum or maximum, is happening at the vertex. And that also, that we see here, dictates what the range is going to look like. So this is for a function that has a minimum, and this is with a maximum. And that leads into the next thing, know how to find maximum or minimum. Know how to find maximum or minimum. And we know that it happens at the vertex. Right, so if you have it in that standard form, like, let's scoot back down a little bit. This form right here, then you know your vertex is at h comma k, then that's either going to be a maximum or a minimum. That's where your max or min is happening. So if vertex is h comma k, which that's what we're saying, you know, those are the letters we like to use for the vertex, then the max or min happens at f of h equals k, right? F at that x value yields that y value. F at that input of h yields a k. Now, is it a max or a min? Well, that's determined by whether your parabola is pointing up or down. If it's pointing up like this, then you have a minimum value. This, you would call this the minimum. If it's pointing down, then you have a maximum value. We also had this little theorem that tends to be quite useful if you only want to know the max or min and you're not really, like, you didn't find the vertex, you don't already have it in standard form, that vertex form. You just get, somebody just like plops down a quadratic equation and says, what's the maximum or the minimum of it? And we had this idea for, so this is specifically for something that's just in this like normal quadratic function form. The max or min happens at f of negative b over 2a. And you have to evaluate what that is. And you also have to say whether it's a max or min based off of whether it's pointing up or down. I'll say if a is positive, right? So if this a is positive, then it's a minimum. And when I say it, then what is it? Then this, whatever this evaluates to, is a minimum. If a is negative, then that means the parabola is pointing down, like this case. Then this value is a max. So if you have your function in that standard form already, because the problem probably already asked you to do it, then finding the max or min, just look at the vertex. Okay, just look at the vertex. Now, if you're doing a problem, like I'm about to show you, one where all the problem asks for is just the max or min, and it doesn't ask you for the standard form or x-intercepts or domain and range, all that stuff, then you can just fall back on this. Let me get some paper. So what kind of problem would do that? Because every single problem I've worked for you in this section so far has been asking for pretty much everything, right? Just starting with this function in ax squared plus bx plus c form and asking for the standard form, the vertex, the intercepts, the domain range, and a sketch of the graph. Well, here's a problem where you might only want to know the maximum or minimum. So let's say this is a real world problem. A soft drink vendor at a popular beach analyzes his sales records This is problem 54 in the text. And of course, you all have the ebook in WebAssign. If he sells X cans of soda in one day, his profit in dollars, because this is like an American beach or an American business, so we use dollars, is given by, now here comes a polynomial function, p of x equals negative 0.001, which is very different from what we're used to seeing, x squared plus 3x minus 1800. Now, let me ask the question, and then I'm going to talk about this a bit. What is his maximum profit per day? Whoops, profit per day. And how many cans must he sell to make that maximum profit? So his maximum profit is going to be whatever the output is, the y value of the vertex. That's what, if in terms of like, you know, the picture, the maximum profit would be the y value of the vertex, and the number of cans to reach that maximum profit is the x value. Okay. So x is number of cans here. Now, I want to talk about this function a little bit, because every single function you've seen so far, the coefficients are just like integers, like -5 or 3 or 2, you know, or even 1 a lot of times, not this 0.001 thing, right? So that's very interesting, but I'll tell you that as having taught some only a couple applied mathematics courses, and especially in the context of applying math to finances, the functions, the quadratic functions modeling profit do end up looking like this. You'll have a very large constant term, right? That's usually negative. This would be his profit, right? If he sold 0 cans in a day, he would lose $1,800. $1,800, right? That would be at p equals 0, or I'm not sorry, not p equals 0, p at 0 with x equal to 0. If he sold x number of cans and if he sold no cans, he's going to lose $1,800 that day. So it costs, that means like this number comes from like, you know, cost of running the vending stand or whatever it is, the business per day, which it must be more than just a little soda drink stand. If he's losing $1,800 per day, it must be like a whole business. And this term does end up the leading coefficient always does end up being very, very tiny. And in this class, we're not talking about, it'd be real fun to talk about like building these functions and talk more about profit and things like that. But that's not one of the things we get to do in this course. But this is not just coming out of nowhere. This function would come from like a supply and demand kind of relationship that he would have to analyze over time, that he would have to know by analyzing his sales records. I wrote sales twice there. I don't know why I did that. And anyways, so this is not just coming out of the blue. This could possibly be a legitimate function that someone would use to model their sales, and it would legitimately be quadratic. Now, all of that being said, all we want is the maximum, right? Well, we know f at negative b over 2a is going to give us the maximum. Or in this case, I'll say p at negative b over 2a, because p here is the letter we're using for our function, p for profit. I know that b is equal to 3 and a is equal to that negative 0.001. Just the coefficients, right? That's all a, b, and c are the coefficients of this function when it's written in this form. Ax squared plus bx plus c. C doesn't matter for this particular thing that we're doing here, finding the maximum. Okay, and by the way, how do I know it's a maximum? Well, they told me in the question, they said what is the maximum, but if I wasn't sure if it was a maximum or a minimum, I just look at the sign of a. Since a is negative, I know this parabola is pointing down, and I do have a maximum value. P at negative b over 2a, well, off on the side, I'll figure out what negative b over 2a is, and it's going to be negative 3 over 2 times negative 0.001. That's definitely a job for the calculator. So 3 divided by 0.002. They're both negative. The negatives cancel, and I'm getting 1,500. 1,500. Just plugging that into the calculator. That's all. Well, I already have the number of cans he must sell for maximum profit. It's 1,500 cans. That's how much he has to sell to maximize his profit. What is that maximum profit for the day? Well, I need to evaluate the function at 1,500. So I plug in 1,500 into the function. Let me add my commas here, minus 1,800. Alrighty. Okay, and I'm going to back the equal sign up a little bit to give myself some more room. Negative 0.001. 1,500 squared is 2,250,000. 2,250,000, that's a 5. And then plus 4,500, and then minus 1,800. I'll go ahead and multiply these two numbers together, which just scoots the decimal out. So anyways, negative 2,250. And now I just have a string of addition and subtraction to do here. So I will make that negative. I'm just using the calculator to do this. I'm being lazy. Minus 1,800. And I'm getting $450. That's the maximum profit for the day. So let me write this down. Where are we at? The maximum profit, maximum Okay. So based off of our math, we have that the maximum profit he can make in one day is $450. And the number of cans he needs to be able to sell to maximize profit is $1,500. Okay. What else can I say about this? You would think that in order you would think there would not be a limit on how much profit he can make in a day as long as he can just keep selling cans, right? You would think that if we did the math on this, we would just find that the more cans, the better, right? If you sell 1,500 and make $450, then sell 3,000 and you'll make even more money, right? But we know that finances and these sorts of things are not that simple, right? They're not that simple. There's a supply and demand issue at play here too. So this is like legitimate math that people are interested in the real world, people that run businesses and stuff. So this is an example of even just a quadratic function, which is kind of it's like a pretty simple function when you get down to it. Because why do I say it's pretty simple? Well, pretty much all the interesting things about it I've written down on like a page and a half for that summary. That's like pretty much like the most you can say about quadratic functions, honestly. Like this is like everything. So well, obviously we could always say more about them, but I'm just saying like relative to other types of functions, they're quite simple, and they're still though very powerful in how useful they are. Okay. So that was a real life problem, just showing you how quadratic functions can be used to model real life situations. And there's a lot of other ways, not just finances, that quadratic functions can be used to model real life. Let's see, what else do I want to say about that? If you're really interested in that stuff, there's a class at JSU called Applied Calculus. And typically that starts off with a discussion on how the functions, the functions that you learn about in 112, how those can be applied to real life. Pretty fun, I think. All right. Let's move into polynomial functions and their graphs. So now we're extending beyond quadratic functions, because 3.1 was quadratic functions and their graphs, basically. So now we want to look at polynomial functions in general. So a quadratic function, recall, was just a degree 2 function. So we could write it as ax squared plus bx plus c. That's like its most basic general form. But a polynomial function in general can have up to n many terms, n being just whatever number you want. As long as it's not infinite, which I don't think you guys would probably even be thinking about that anyways. So, but it is a point to be made. Polynomial function can have any number of terms as long as you're not talking about an infinite number of terms. So that gives us a little bit of an issue because it's really easy to write down a general form for a quadratic function. I can just it's just x squared, x, and a constant, right? and I can just use A, B, and C for the letter coefficients. But here for polynomial functions, I can have like 100 terms. I could have 1,000 terms, right? So what do I use? I don't want to use letters necessarily, like A, B, C, D, etc., because there's only 26 letters. So instead, I use just the letter A and subscript it. So I give it an index to keep track of which or how many there are. So we'll say P of X. Now this capital P is standing for polynomial right now. Okay, so some general polynomial function can be written as, so first coefficient is A sub n, so that's the leading coefficient there, and it's attached to the highest order term. So n is the highest exponent here. So the next term would be A, again, using the same, I'm just going to keep using A, and I'm keeping track of which A it is by its little subscript. And this one, it's the next term, so it decreases by 1, as does the exponent. Then we have A sub n minus 2, x raised to the n minus 2. Okay, so all this a sub n minus 1, they're just numbers. That's all they are. They're just numbers. And the n's in the exponent, they're decreasing by 1. So like if this was a 5th degree polynomial, it would be x to the 5th, x to the 4th, x to the 3rd, all the way down to the last terms. Now, since I don't know how many this is, because this is a generic polynomial with just n number of terms, I say dot, 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 just to kind of sweep all the stuff in the middle under the rug. And the last couple terms would be a sub 2 x squared, see the matching there, a sub 1 x to the first power, and then the last one is a sub 0 with no x term. Technically it's x to the 0, right? But recall that x to the 0, anything to the 0 is just 1, so it's not necessary to write it down back here. Chop all these terms away, and I just end up with that quadratic equation there, or quadratic function there, right? X squared, x, and a constant. But this is now expanding to a generic polynomial with n many terms. All right. We call those a's, the coefficients. I've already been using that terminology, right? These are the letters, the numbers rather, that are represented by the letters that are attached to the individual x's are called coefficients. A sub n is the leading coefficient. It's the most important one because it's attached to the most important term. We call a sub 0 the constant term. Constant meaning it's not variable. It doesn't have an x attached to it. It's the constant term. And we call a sub n times x sub n, so the whole thing, not just the coefficient, but the whole thing, the leading term. Okay. Last thing, I forgot one last thing. Let's say we call n the degree of the polynomial function. So if the leading term has x to the 5th in it, like x to the fifth, then n would be 5. 5 would be the degree. We would say it would be a fifth degree polynomial. All right. So what we're about to do is we're going to talk about graphing these things. How can you graph just some generic polynomial? That's the tool set that we're going to be building in this section. And almost all of the information is going to come from that leading term because it's the strongest term. Both the leading coefficient and the degree on that leading term, that n and the leading coefficient, they are going to be like the king and queen of the polynomial function, right? Or the king and king, or the queen and queen, depending on, whatever. Okay, so all of these other terms you can think of as being weaker. So the leading term is going to dictate the shape, the overall shape of the polynomial function graph. Why do I point out a sub 0 then? Why did I even, where did I say? Right here, a sub 0 is the constant term. A sub 0 is just nice to see because, well, what does it give you? It gives you the y-intercept of the graph, just like that. Like you can just look at the back and say that's going to be the y-coordinate of the y-intercept. And we notice that for quadratic functions too. So it's not nearly as useful, but it's just kind of it's such an easy thing to point out that that we like to point it out up front. All right, let's practice making sure we all can identify these parts. The leading coefficient, leading term, and constant, just for practice. Let's say that p of x is equal to negative 7x to the fourth plus 3x cubed minus 8x squared plus x plus 5. All right, so we have the notes here. Though hopefully, you have it written down anyways. So I'm going to get you guys involved here to tell me the leading coefficient, leading term, and constant. And we'll also point out the degree of this polynomial function up here. So Makira, what would the leading coefficient of this polynomial be?
-7.
That's right. Leading coefficient is -7. Oops. -7. And Maya, what would the whole leading term be?
Can you say it again? You were breaking up.
What would the whole leading term be? Whoops, I didn't mean to. I started writing it. What would the leading term be?
7.
What's that?
7.
It would be, the whole leading term would be -7x to the fourth. Okay. So not just the coefficient, which is -7, but the whole term. And we'll say its degree is 4. And then the constant, I'll go ahead and write down the constant is 5. Cool. Okay, cool. So that's the things that we're going to need to know how to identify to be able to graph these, because the rules for graphing these polynomial functions are all going to be centered around what's happening with the leading coefficient and the leading term and the degree. Excuse me, and the degree. Okay, let's see. Let's do another one. Let's do another one where I mix it up a little bit just for fun. Let's say 3 minus x squared plus 4x to the 7th. So, Kimberly, what would the leading coefficient be?
4.
Yeah, good. The point being in this problem is that leading coefficient doesn't have to be up front, right? It's the number attached to the highest degree term. So yes, it would be, thank you, it would be 4. We like to have these polynomial functions written in descending. You know, we would prefer to have it written as 4x to the 7th minus x squared plus 3 with the degree descending, but sometimes they're not written like that. Honestly, like if they're not written like that, it's just because the problem is trying to be a little bit more difficult. Excuse me. But pretty much like I've found in the real world, like if you're building your own polynomial functions to model something, you're going to put them in order, right? You're not going to decide to put them in a crazy order just to mess with yourself later or something. So, but it is nice to know that if it is out of order, then you're just looking at that thing that has the highest degree, the term that has the highest degree. And by the way, the leading term for this would be 4x to the 7th, that whole leading term, and the constant would be 3. All right, good. Now, oh, wait, I know, we need to look at some other ones. I'm going to keep going with this. Practice identifying the leading coefficient, etc., etc. Let's do another one. P of x equals x times x minus 2 times x plus 3. What about something that's written completely wacky like this? It's actually a nice form because it's already factored for us. But how can I quickly identify the leading coefficient and whatnot? Well, maybe it's not so easy to see. How about I find the leading term first? Because if we know the leading term, then we can just pull its coefficient off. That'll be the leading coefficient. And I'll also find the constant. Well, the leading term is going to come from multiplying all of the x terms together. So when it's written in this form, leading term comes from, in this case, x times, the second one is x times x, which is x cubed. This x times this x times this x. That's going to be how I get the highest degree term, right? Not any other combination of x's and the -2 or the +3. The way to get the leading term is to multiply all of those x's together. And in this case, all of their coefficients were just 1. So it just ends up being x cubed. So my leading term is x cubed. And my leading coefficient then, well, what's the coefficient on there? It's just a 1. Not very interesting there. Now, what about the constant? Well, the constant is going to come from the product of all of the constant numbers inside the factors. So there's nothing here, so I won't write anything for the first one, for that just x, that it's going to be -2 times 3, which gives me -6. All right, so let me say some stuff about this. Note that I could just multiply this out, right? I could do it. You guys could do it. If you had a little time, you could say, well, note that I could just say P of x is equal to, here, I'm just going to say real quick, x squared minus 2x plus 3x. X cubed. I'm doing it in my head. One moment. -2, +3 is an x. So, and then. Oh, I just realized I made a mistake over here. Sorry. over here, the constant comes from the product of all three of the constants, but if there's not a constant here, I don't know what I was thinking, then you write a 0 as a placeholder, and then that constant will end up being 0, which we see here. There's no constant term. There's no constant term. Sorry about that. I was like, my mind was elsewhere or something. I don't know. Constant comes from the constant term that's attached to this x by addition or subtraction, which technically there's nothing there. That's why I wrote a 0. And then this number attached to this x by addition or subtraction, which is the -2. And then you see the +3 is there as well. And of course, none of the 2 and the 3 don't really matter. The 0 is taking over here in the product, giving us just a 0. And we see that reflected here. So what's going on here with this, with these two little tricks that I wrote in blue? What I'm saying is I don't really care about these middle terms. I don't really care about these middle terms. All I care about is the leading term, because that's going to contain all the information about my graph, or at least most of the information. And I also like to know the constant term because, again, that tells me the y-intercept of my graph. So what these little tricks save us from doing, since I don't care about any of these middle terms, these two tricks save us from having to multiply this all out, which in this case is not too bad. You guys could do it. You know, you could get from here to here. But what if there was like 5 more, right? You don't want to deal with that. Even if there was just 1 more, then it starts to get really annoying to multiply it out. So these little tricks save us a lot of work. Let me do another one here. I'll do it on the same page. Let's do another one. Let's say 2x plus 3, x minus 4, and 7x plus 2. Okay. So if I'm trying to find my leading term, I know that there are 3 x's here that would end up getting multiplied together. 3 x's, a 2x, a single x, and notice I am bringing the coefficients with them. So a 2x, a single x, and a 7x. And Aviana, what does that give me? Does anyone know? Oh, go. Yes, sorry, go ahead. Yeah, 14.
Is the 14x squared or is it to the third?
To the third. To the third.
Gotcha.
Yes, because it's x times x, which would be x squared, and then 1 more x, so x cubed. Good. Yes. So that's our leading term, which we got without having to multiply it all out. So my leading term is 14x cubed. So, okay, that means my leading coefficient, I can go ahead and write that down. Once you have your leading term, your leading coefficient is just the number attached to it, so just the 14. And my constant, well, I don't have that yet, but I can go find it. My constant would be coming from the product of the three numbers attached to the x's by addition or subtraction inside of each factor. So I'm seeing a +3, a -4, maybe I should wrap it in parentheses, and then a +2. So +3, a -4, and a +2. And that's going to end up being -24. Yes, -24. So my constant is -24. Cool. Now, that is a lot faster than multiplying this all out. All right. So let's try another one. In fact, let's see how this goes. We'll do like a little, oh, is there a question? I got a chat. Actually, I think the chat might be from someone in a different class. Yes, okay. I'll read that later. All right, so P of X. So what I want to do here is just to emphasize how good these tricks are and to let you guys have some more practice using them. I will give you a polynomial function, like similar sort of to this. And I'll ask for the leading term, leading coefficient, and constant. And as you guys get the answers, you can either pop them in the chat or just speak up and say you have the answer or raise your hand. And what I'll do is I'll try to find the answers not by using tricks like these little tricks over here, but by actually multiplying it all out, and we'll see who can get there first. So let's see how this goes. So it's like a race. I don't want to think too much about what I'm giving as the numbers because, and I'm only going to do 3, again, just 3. But I'm going to make it a little bit more interesting. It won't be exactly like the last one. So let's say, okay, here we go. As soon as you see me write it down, you can start trying to find the leading term, leading coefficient, and constant. Let's say 2x squared, so plus 1, and then times 3x minus 4, and then let's do a nice simple one back here of x plus 2. All right. And I'm going to try to multiply this out the long way. So you guys are trying to find by using the tricks. I do not recommend trying to follow along with what I'm doing because you'll probably end up getting confused. Well, maybe not. Maybe not. I didn't need that parentheses there. Let's see. Okay, I've got my answers. Did I beat you guys, or maybe just no one was brave enough to speak up because they didn't know if they were right or not? Anyone want to say what they got for the leading term?
I got 6.
But the whole leading term. 6 is the leading coefficient. What is the leading term?
6x to the 4th.
Right, 6x to the 4th. Good. That's what I got as well. And the leading coefficient, so I'll just say leading co for leading coefficient, is 6. And then the constant, did you get -8 as well?
I hadn't gotten to that one yet.
Okay. So let's look at where this leading term came from. It would be, so this is the leading term. What we have to look at is the product of the 3x terms. So I'm looking at 2x squared, a 3x, and a single x, and that's giving me 2 times 3, so that's 6, well, times 1, but 2 times 3 times 1 is 6. And then x squared times x is x cubed times another x is x to the 4th. There it is. And then the constant term is going to be the product of the 3 constants up here. So 1, -4, and 2, giving me -8. Oh, -8 there. All right. But what was the point of this exercise? The point is that this is way easier, right? And if none of the terms in the middle matter too much for graphing the polynomial function, then I don't need any. I don't need to know that the central term is negative 13x squared and there's a 2x and a 4x cubed, because they're not that important in the grand scheme of things. So these tricks are going to be what we use to graph our polynomial functions. All right, let's look at how are we doing on time? 10 minutes, okay. Yeah, let's just talk a little bit about interpreting the degree in, well, here, how about this? What to do with the leading term information. So now we know how to get it for different types of polynomials, but once you have it, what do you do with it? Well, here we go. If degree is even, then both legs, quote unquote, of the function graph, of the graph, I'll just say of the graph, point in the same direction. I'm not going to say point up because I don't know if they both point up or both point down, right? But they point in the same direction. And I'll say as a little next idea here, if leading coefficient is positive, they point up, right? If leading coefficient is negative, they point down. We've seen this with quadratic functions, right? Quadratic function has degree 2. It's even, and the legs either both pointed up, like this kind of parabola, or they both pointed down, right? Like this. In fact, we've seen this in section 2.6 when we talked about transformations of functions. We know like an x squared and an x to the 4th and an x to the 6th graph, they all kind of look similar, right? They all kind of have that same shape. And then we have if degree is odd, then legs point in opposite directions. If the leading coefficient is positive, I gotta think about how to say this. Left leg points down and right points up. Right leg points up. So that means like this kind of shape, right? We've seen that kind of cubic. We've seen cubic graphs that do that, right? Left side is pointing down, right side is pointing up. If leading coefficient is negative, and then the opposite. Right leg, no, let me go. Left leg points up and right leg points down, like this. Now, what we're going to do next time is introduce some new notation that's going to seem weird, but this is basically the idea. These are the ideas. Let's see, can I get it all? Scoot it back down, get all this on one page. First of all of this information I'm talking about, whether the degree is even or odd, and whether the leading coefficient is positive or negative, that's coming from leading term info, right? All the things we just investigated, all of this is these are questions that would be answered by just having that leading term in front of you, right? Knowing its degree and whether or not it's positive or negative. And this is how to interpret that information on a graph or for the purpose of graphing the polynomial function. And so yeah, next time we will look at applying some more technicality to this. Instead of just saying it in words, we're going to have some symbology with arrows and infinity symbols. Like for just to give you an idea, like for this case, degree being even, leading coefficient is positive, we would say as x tends to infinity, p of x tends to infinity. As x tends to negative infinity, p of x still tends to infinity. So we'll talk about like what the heck that means and what's going on there. But each one of these 4 cases, this 1, 2, 3, 4, will have its own little set of special symbology for us to write down. And yeah, we will do that. We will talk more about that next time. Okay, you guys are good to go. Stick around if you have any questions. Oh, I need to, well, you can still go. I'm going to give you some review problems, but I'll just put them in the chat. So you're good to go.